Next up, we have Matt Uliana. He is the principal hydrogeologist for Interra. His fields of focus are physical and chemical hydrogeology, computer modeling of groundwater flow, supply studies, and more. There's a that's just scratching the surface of his experience. So again, I encourage you all to visit that live program so that you can see his full background. Matt is here to teach us about injection wells and how GCDs can protect water quality, what they might want to consider. So with that, if you are ready, Matt, I will pass it on to you.
Thank you.
Thank you.
Thank you, Julia. Thank you all for attending and participating in this today. So as Julia said, I am a principal hydrogeologist with Interra Incorporated in Austin. I've been in Austin since the early 90s. I did my graduate work at the UT Austin, and I've been working on water resource, groundwater, environmental related projects in Texas since the mid 90s, and have been involved in projects associated with groundwater conservation districts for much of the last 20 years or so. So I'm pretty well aware of what groundwater conservation districts do and what the big issues are that they have and what are things that are of concern to them and what their mission is. But I was just about a year ago, I was involved in a project that was involved reviewing an application for a new saltwater disposal well in one of the districts, and it made me realize that there are some things here that could be of concern to a lot of the districts that they're not realizing. So that was the impetus for doing this presentation, just to give you an idea of what these disposal wells are and what sort of water quality issues they could potentially pose to groundwater conservation districts and what you need to be aware of moving forward. So a little bit about the, let's see here. There we are. So a little bit about what I'm going to be talking about today and the overall organization of the talk. First of all, we're going to define what injection wells actually are and define the classifications of them. And they're basically classified based on their function, what it is they're being used for. And then those classifications in turn are going to have some implications for what agency is regulating them, how they're designed, and what sort of permitting process is involved in each one of those. And with each one of these injection wells, a big part of the permitting and regulatory process goes into how the wells are designed and constructed and operated in order to protect usable groundwater, right? And that's really the focus of a lot of the permitting process and a lot of the regulatory framework that these wells are built around is how the wells will protect underground sources of drinking water. And you're going to see this term underground source of drinking water come up a number of times in the presentation, and I'll give a clearer definition of what that means in a little bit. And so we'll talk about how these wells are designed to protect underground sources of drinking water. What are the things that could potentially go wrong that can impact underground sources of drinking water? And then what the procedures are for protesting applications. And by protests, I don't just mean walking around with a bunch of signs outside. I mean the actual formal process that you can go through for filing a protest to stop an application in case you're concerned about that application having a negative impact on the groundwater within your jurisdiction as a groundwater conservation district. So just want to start off real quick, a little bit of shameless self-promotion here. If I don't do this, our marketing department is going to try to have me fired. So just a little bit about who Interra is. We are a geoscience and engineering consulting firm that's been around since mid-70s, all employee owned. Our corporate headquarters is in Austin, Texas, but we have offices around the country as well as a couple of offices in Europe. Involved in a lot of service areas related to natural resources. We do a lot of water resource work. We do a lot of environmental compliance consulting, remediation design, cleanups, that sort of thing. We've got a division doing coastal engineering. And a lot of what the company was founded on and what we still do today is waste isolation associated with radioactive waste. So the idea of putting away radioactive waste from nuclear processes and so on and so forth. With the Austin office in particular has a lot of experience in Texas doing water resource projects and a lot of experience with groundwater conservation districts. A number of our staff, including myself, are actively working as hydrogeology consultants with districts within the state. And we've worked with districts all over the state, either directly supporting their efforts or working with applicants for permits or working on the groundwater availability models that the districts use for their water availability determinations. And Interra has been involved in the development and updates of a number of those. And our corporate mission statement is delivering excellence with every solution. So we promise that if you get a solution from us, you'll get some excellence along with that. So everybody here who's in this talk knows what the groundwater conservation districts are, and you know what the mission of them is as well as I do. And the mission is really centered around managing the groundwater resources within your jurisdiction, protecting the property rights of the landowners within your jurisdiction. And a lot of that comes into this balance of conservation and development. So that's really what we've all been talking about, especially for the last decade or so, is that groundwater conservation districts are all about determining how to develop the resource in a way that can conserve the resources for the future, but support the development of groundwater needs of the state. And we have this mandate to use the best available science to do that. So we're looking at using the best models and understanding of the aquifers and scientific methods to balance that conservation and development. But along with this idea of conservation is the regulations define what conservation means, and conservation means avoiding waste of groundwater. And that's defined in the regulations as not just the volumes and amounts and availability of groundwater, but also the quality of groundwater. So districts have a mandate to adopt management practices that will not contribute to pollution or degradation of groundwater resources of the quality of groundwater. So, which is something that I was aware of, but didn't really think about too much until I got involved in this case involving this injection well application. Now, in my experience going beyond groundwater conservation districts, I've done a lot of work on injection well design and permitting and modeling and that sort of thing. So I have a decent understanding of how injection wells work and an understanding of what sort of things could go wrong. So that's what we're going to talk about today, is what the different types of injection wells are and how they're designed and permitted and what sort of concerns they have for districts. So all the injection wells are broken up into 6 individual classes. Now, I just put this picture here to be funny. We're not talking about the kind of classes that your kids aren't in right now, which they should be, but kids aren't in. We're talking about the classifications of wells, and they're classified based on the purpose for the well. So the first class are disposal wells, and these are disposal wells that they're designed to dispose of wastes that are generated through industrial or municipal processes. So an example is you have say a chemical processing plant that produces a waste stream, and they can get a permit to design and install and maintain and operate an injection well that injects that waste deep into the ground, deep into the subsurface, into a reservoir that's capable of accepting and sequestering it. The Class 2 wells are generally also disposal wells, but Class 2 wells are all injection wells that are related to oil and gas development and production. So this includes disposal wells that are associated with saltwater. Whenever you have oil production and development, there's going to be a considerable amount of saltwater that's produced along with that, and that has to go somewhere. So you're typically dealing with brines that can be 3, 4, 5 times the salinity of seawater, along with all the other stuff in them. So that needs to be disposed of. So any wells that dispose of saltwater that's directly produced from oil and gas development, those are Class 2 wells. This also involves hydrocarbon storage wells, so wells that are used for storing natural gas and salt plumes, that sort of thing, or wells for enhanced recovery. So in older oil fields where production starts to decrease over time, you're not getting as much from your production wells, so you may put in some injection wells, pump a bunch of fluid in there to essentially push the leftover oil and natural gas to those production wells. That's what we call enhanced recovery. So those injection wells are also considered Class 2 wells. Class 3 wells are wells that are used for mining soluble minerals in the subsurface, things like salts, elemental sulfur. And this basically involves injecting superheated fluid, superheated water down there, dissolving out whatever you're trying to get at, pumping it back up to the surface, and then evaporating out all the salts or minerals in there. Class 4 is wells are for disposal of hazardous or radioactive waste into actively used underground sources of drinking water. Now, obviously, you hear this and you say, well, that's a terrible idea. Why would anyone ever want to do that? Why is there even a class for that? You don't want to be pumping waste into aquifers that people are actively using. And that's true. And these types of wells are generally prohibited. They're prohibited in Texas and in most states and areas they're generally prohibited. But the reason that this class exists is because there can be instances where you have a situation where you have no choice but to dispose of hazardous or radioactive waste in an underground, in an aquifer that's actively being used, because leaving them on the surface is worse. And hopefully it's a temporary situation, that sort of thing. So you're not going to see these wells anywhere in Texas. It's just a classification. You want you to be aware of that. It's a classification that's there just in case you have these extreme situations. Class 5 wells are for injecting into an underground source of drinking water, but not associated with disposal and not associated with anything that's hazardous or radioactive or otherwise could be considered a contaminant. So this can include disposal operations associated with removing stormwater, draining stormwater directly into aquifers, septic if it's associated with a treatment process. It also covers geothermal, pumping out hot water and then extracting the heat and using that to develop energy, and also aquifer storage and recovery, or ASR, which is this process of taking surplus water on the surface, injecting it into an aquifer so that you could pull it out at some point in the future when you have a need for water and surface water is scarce. So that all falls under Class 5. ASR operations are becoming more and more popular. You've probably heard about those, and a number of you are probably seeing them within your districts. And then the Class 6 wells are ones that are directly associated with CO2 sequestration. So that's the idea of taking carbon dioxide produced from some industrial process and liquefying it and then injecting it into an aquifer, or into a subsurface formation for long-term sequestration so that it doesn't go into the atmosphere. And that has its own separate class. Now, for what we're talking about in this meeting today is really going to focus on Class 1 and Class 2 wells, because those are the ones that are associated with waste disposal. Those are the ones that occur within the state and occur in some of your districts right now. And those are the ones that could potentially lead to water quality issues within your districts. The other ones, potentially solution mining, and these other ones could potentially cause water quality problems, but this is really the ones that we're going to focus on today, because these are the ones that are actually significant. So in terms of understanding the wells, you got to kind of understand what the regulatory process is, because if there are any issues, you need to start by going through the regulatory process. And the different wells are managed by different regulatory agencies and different regulatory frameworks. So it all starts at the federal area through the Environmental Protection Agency and through their underground injection control program. So the Environmental Protection Agency initially set up all the regulations to govern these injection wells, and that regulatory framework is really focused around designing and constructing and operating these wells in a way that they don't endanger underground sources of drinking water, right? So they define endangerment as anything that causes the movement of fluids into those sources of drinking water that could result in violation of primary drinking water standards. In other words, you contaminate them and exceed the standards that constitute acceptable drinking water, or just in any way adversely affect human health. So even if it's not drinking water standards, if it's still getting into the subsurface and affecting wetland ecosystems or something like that, that's all built around it. So basically the idea is that these wells have to be designed so that you're not getting contaminants getting into underground sources of drinking water. For the EPA permitting process, any wells that inject wastes that are considered hazardous in Class 1 through Class 1 wells are regulated under this RCRA Act and the Safe Drinking Water Act. And so basically, the concept of hazardous waste, that's defined by the RCRA Act, and there's specific definitions for specific chemicals or specific results of the chemicals, what they could do if you come in contact with them, and so on and so forth. So if your waste disposal, if you have a Class I well and the waste disposal contains any contaminant that can be considered hazardous, then that has to be permitted by the Environmental Protection Agency. And it requires something called a no migration petition. So no migration petition is the regulatory act that you demonstrate, do a technical demonstration that any contaminants that are injected by this well are not going to reach an underground source of drinking water over the lifetime of that contaminant. So you develop the contaminant will exist for thousands of years, tens of thousands of years. You got to demonstrate that it's not going to move that far in that amount of time. Now, the EPA has also established permitting standards for all the non-hazardous wells, and they basically set up a whole framework for regulating these wells. And states have the option for non-hazardous wells of requesting primacy in regulating. And so what that means is that the states can come along and say, we're going to regulate these ourselves. So we're going to put together a set of regulations, and we're going to determine, we're going to issue permits at the state level, and we're going to control all that at the state level. And the only real consideration here, the only thing that the states need to do is that the state standards must meet or exceed the federal standards. So for things like how far the contaminant, for things like how much pressure buildup you can accept, how things need to be constructed, the state standards have to be equivalent to or in excess of what the federal standards say. Okay, so now we're going to move to Texas and the Texas Water Code and regulations at the state level. So all the injection wells within the state are all covered by Chapter 27 of the Water Code, which is sort of in general known as the Injection Well Act. And so the Injection Well Act is going to define what injection wells are and give the formal definitions of your injection wells. And so the idea is that injection wells are something constructed for actively introducing fluids into the subsurface, and that just excludes any surface excavation. So if you got an open pit that you're putting water in, or if you're doing surface application of waste for remediation, that's not governed as an injection well. This is just for constructed wells that go into the subsurface and introduce fluids into the subsurface. The Injection Well Act defines the regulatory jurisdiction. It defines which state agency is regulating which types of injection wells. And along that, it provides what the permitting requirements are for each agency, just in general. And then the agencies themselves will develop what the specific construction standards are, what the process is for getting applications in, how long the permits persist, and when you need to renew them, and so on and so forth. So within the state, there are two agencies that are governing underground injection well. The Texas Commission on Environmental Quality and the Railroad Commission. So the Railroad Commission is involved in regulating everything related to oil and gas and coal and just in general those types of energy resources. So the Railroad Commission regulates and permits. They're responsible for all of the Class II wells. So if you recall, the Class II wells are the ones that are just associated with oil and gas development. The Railroad Commission, they then necessarily regulate and permit those types of wells, right? They can do all the Class II wells. If there are other wells that are associated with energy resources in a certain way, then they can have jurisdiction over those. But basically, Railroad Commission does the Class II wells. The TCEQ then is in charge of permitting and regulating all the other wells. Now, the Class I hazardous wells, they do need to have EPA approval and the EPA no migration petitions, but any Class I well that's not hazardous is solely governed by the Texas Commission on Environmental Quality. The permitting process in each agency, they're very different from each other. The way they deal with issuing permits, the way they deal with evaluating applications, it's a very different process. And for me, I had a lot of experience dealing with the TCEQ, developing Class I applications. And over the last couple of years, I've gotten involved in these Class II applications and the whole process, and I've come to realize that it's drastically different type of process, right? And for each process, along with the applications, when applications are filed, there's a review period and there's opportunities for stakeholders to protest those applications. And any well that's going in within the jurisdiction of a groundwater conservation district, well, that makes the districts a stakeholder. And so you have opportunities to protest those applications. So let's talk a little bit about the permitting process for each and sort of compare and contrast how they work. For the Class I permits in the TCEQ, this process is pretty complicated. It's a long, involved process that requires really, really extensive technical demonstrations. There's a lot of modeling, a lot of analysis, a lot of demonstrations for what's going to happen once those fluids are injected into the subsurface. One part of the Class I permitting process is that they require something from the Railroad Commission called a no harm letter, which is just a statement from the Railroad Commission assuring that this injection well won't have any impact on oil and gas reservoirs. So there is some connection between the TCEQ and the Railroad Commission in that respect. The TCEQ governs basically all the other processes involved in permitting those wells. So they have real specific regulations for constructing the wells, and those construction regulations are really all about maintaining the integrity of the well so that the wastes that go into the well will go in and out into the intended injection reservoir, that intended formation that's thousands or even tens of thousands of feet below the surface, and not go anywhere else, not leak out into an underground source of drinking water. And we'll talk a little bit in general about what those construction regulations and standards are here in a moment. These applications involve a seismicity review. So one of the big issues that's come about with injection wells is they're inducing seismic events in certain parts of the country, generally in areas where you already have pre-existing seismic risks, where you have you already have earthquakes occurring. So there's a review of what the overall seismicity is in the area that the application is going in. There's calculations involved for determining what the maximum allowable injection pressure is at the injection well. So the idea is that when you're injecting fluids into the subsurface, there has to be additional pressure at the surface to get them into the formation. If that pressure gets too high, it can result in hydraulic fracturing of the formation. So you can frack the formation if the pressure is too high. So the TCEQ requires a set of calculations that are a function of how deep the formation is, what the static pressure is in the formation, and what the properties are of the rock that make up the formation. So you have to do this calculation to determine what that injection pressure is, and then that's built into the permit. Not that the operators are not allowed to exceed that pressure. There's also a considerable amount of modeling goes on to simulate and predict how much pressure is going to build up in the formation and how far the plume of injected wastes are going to move over the lifetime of the well. And the lifetime of these injection wells are typically 30 years. So along with this pressure buildup calculations, there's an area of review that goes in, which is 2.5 miles, or the cone of influence that's determined by the pressure buildup modeling. And so the cone of influence is basically what they do is they calculate how much pressure is going to build up and where are the points in the vicinity of the well where that pressure is going to be sufficient that if it encountered an open borehole, say an abandoned well or something like that, it could push fluids from the injection reservoir all the way up to the surface and encounter an underground source of drinking water. So, and part of this area of review is looking in that area and finding what all the records are on existing wells that go down and penetrate the injection reservoir. So there's a formation down there that you're injecting in. If there are old oil wells or even existing oil wells in the area that penetrate that, those need to be evaluated to make sure that they have sufficient construction standards to avoid any type of avenue from injected waste into the surface. And then these go through an annual testing regime where the mechanical integrity of the well is tested. They go in and make sure that the well is still maintaining pressure, is maintaining the fluids containment within the well. You're not getting any fluids that are coming out. And they go through a 10-year renewal cycle. So every 10 years, the well have to go through the permitting process again, and all the models have to be updated, and so on and so forth. There are a relatively small number of Class I wells within the state, especially compared to Class II wells, which we'll see those numbers in a little bit. But the Class I wells are somewhat limited, primarily because the permitting process is really complicated. There's extensive technical demonstrations and evaluations, like I just talked about, so it costs a lot. That whole permitting process is really expensive, and putting in a well is extremely expensive. So these only go in if it's actually worth it for the people who are doing it. And they're primarily located by where the industries are and where the available injection reservoirs are. So in certain parts of the state, you're just not going to find a formation at a reasonable depth that's going to allow you to inject fluids in it. A lot of them, it's also based on what the other available disposal options are, because these things are expensive to maintain. And so doing the economics of that, it has to be worth it for them to do so. So again, there's a small number of these, a very laborious and extensive permitting process. For Class II wells, the permitting process is a lot simpler and it's much more streamlined, and it's really based around forms where they have developed sort of standardized formulas for evaluating things like injection pressures and injection and fluid injection rates and that sort of thing. Right. So for Class I wells, the well design criteria is really pretty similar to the well design criteria for the Class I wells, with that focus on protecting underground sources of drinking water and identifying where those underground sources are and making sure that the well is completely sealed so that you're not getting any of the injected wastes impacting your underground sources of drinking water. These permit applications generally don't involve any sort of pressure buildup modeling. The maximum allowable injection pressure at the surface is typically based on the depth, and they have a relatively conservative equation so that will minimize what sort of injection pressures are allowed at the surface. And this is one thing that I've personally looked at in comparing what their maximum amount allowable injection pressures are just solely based on depth compared to injection pressures that I've calculated using the TCEQ type of formulas. And the Railroad Commission formulas are actually considerably more conservative than that. They don't really allow for nearly as high injection pressures. The area of review is much more restricted. You're only looking at a quarter of a mile around any injection well, proposed injection well. So there's less of an opportunity for them to encounter any existing wells within that area of review. They involve seismicity evaluations, and they also involve modeling to look for seismicity risk, which is something that's relatively new. Because a lot of the seismicity issues associated with injection wells have really been associated with Class II injection wells, with those saltwater disposal wells, especially because they tend to be focused. There tend to be more of them, and they tend to be focused in relatively restricted areas. So there's a whole component of evaluating what the existing seismicity risk is, and if this injection well is going to potentially exceed the pressures that can cause slip and create earthquakes and that sort of thing. So there's a considerable amount of that involved in it. And these undergo mechanical integrity testing, just like the Class I wells do, although the mechanical integrity testing is not quite as frequent as it is for the Class I wells. So we showed that the Class I wells were somewhat limited in terms of the numbers and their locations. For Class II wells, there are wells that are solely for saltwater disposal. There's over 35,000 of those within the state. The wells that are associated with enhanced oil recovery, so those are the wells that are associated with pumping fluids into active oil reservoirs in order to stimulate recovery and get more oil out, push oil to the producing wells. There's over 84,000 of those. And you'll notice that there are some patterns that show up in where all these wells are located. Well, as you might expect, those wells are all located in areas where we have active oil and gas production. So for the saltwater disposal wells, those typically go in as close to the production wells as possible, because if you're producing a lot of salt water, you don't want to be trucking it all the way across the state to dispose of it. So those tend to be located in areas that are associated with active production. The enhanced oil recovery wells, by definition, they're inactive oil oil formations and natural gas formations. So they're also going to show up there. So this gives you an idea of where the most significant risks are and issues where you could potentially have oil and where you could potentially have Class II wells going in the future. So we mentioned that these wells are designed in order to try to minimize or eliminate the possibility of the injected fluids getting into underground sources of drinking water. And so that process, that construction design process, is really associated with using multiple casings and properly cementing in between those casings so that you can eliminate any interaction between the fluids that go down in the injection well with formations that are containing underground sources of drinking water. So let's say we have, here's a hypothetical situation. We're looking at a cross section. This is the ground surface up here. We've got a bunch of different formations down here. We've got confining units with a few aquifers, a few oil and gas producing zones in this injection interval. And typically we're seeing our depths of our unconfined aquifers, usually around 100 or a couple of 100 feet. Our deepest underground source of drinking water, maybe a few thousand feet. Our injection intervals are usually 5 to 15,000 feet or so. The Class I wells are usually in this 5 to 10,000. Class II wells are going deeper and deeper because they're having trouble getting permits in some of those shallower formations because a lot of them are being overpressured at this point. So in this kind of a situation, we may design a well, and this is just hypothetical. You may not have any oil and gas producing zones. You may only have one aquifer here at the surface and nothing else that's usable, but this is just a hypothetical situation to show all the different components that you could be potentially encountering in one of these wells. So this is a cross section showing an individual well, and these lines here represent the individual casings. So over here you can see there's a conductor casing at the first, surface casing, intermediate, so on and so forth. So that's what these represent. So here's some labels. So we've got this blue here is the injection tubing that goes down. And the way these are drilled is you use a large diameter bit. This is usually something that's about 2 feet across or even more, that goes down to just below the unconfined aquifer, generally goes down to below any unconsolidated sediments. So you've got soils and you've got sand and gravels and that sort of thing. So you get into solid rock. They'll drill that down and put in this large diameter conductor casing, cement that into place, and then go in with a slightly smaller bit, drill that down to below where the deepest known underground source of drinking water is, and cement all that off, and then go back in that with a narrower bit that goes all the way down to this depth, to basically to the top of where your injection interval is, cement that in, and then you can go down in that with a shallower or a narrower bit that goes into the injection interval, and put in this tube with the blue here. It represents the injection tubing. This open space out here between the injection tubing and your intermediate casing is the annulus. That's an open area, and then there's cement that goes in around these. So for Class I wells, this needs to be cemented all the way down to here. For Class II wells, there's this all needs to be cemented at the very least to the depth of the deepest underground source of drinking water, and the intermediate or long string casing, this can remain open to the formations with the exception of at least 100 feet above the top of the injection interval, providing there are no oil and gas zones. If there's an oil and gas zone, then those zones need to be cemented off as well. But there's a slightly more relaxed regulations concerning the casing down here. But ideally, you want to have all of this cemented off so that it's all sealed. So anything that goes down through the injection tubing is just going out into the injection interval through perforations in this. So typically what they'll do is this is a solid piece of steel pipe, and you go down with shaped charge and you punch a bunch of holes in here right at the zones that you want. And so those are the zones that are open. So anything that gets injected in here just goes into this formation. And all of this cement here should be sealing this off from what goes in here. There's typically fluid that's filled up in the annulus, and this is kept with a positive pressure. So the pressure here is higher than the pressure that's in here. So if there is anything where this would happen to break or a seal would come out, the pressure in here would still hold all the injected fluids in here and then go into the perforations. So this is a real typical kind of construction that you see. And with cement being used to seal off all the individual zones, so that ideally anything that goes down into this is going to go into the injection interval down here and stay in there. And these confining units should maintain the pressures down here and maintain the fluids and keep the fluids from moving up towards the surface. Along with the Railroad Commission, with the Class II applications, is the Railroad Commission will require that the applicant get something called a groundwater protection letter, a groundwater protection determination letter from a group called the Groundwater Advisory Unit. So what the Railroad Commission has done is, throughout much of the state, at least in areas where there's a lot of Class II wells going in, they've defined where the depth of usable underground water is, and they define a couple of things. There's a depth of fresh water, and fresh water is designed as anything that's less than 1,000 milligrams per liter of total dissolved solids. There is something called the base of usable quality drinking water, and that's defined by the contact between any fluids that are less than 3,000 milligrams per liter total dissolved solids and any fluids that have higher total dissolved solids. And then they define the underground source of drinking water depth as the depth where the fluids reach a total dissolved solids of 10,000 milligrams per liter, right? And so they determine, this letter determines what those depths are, and then that in turn goes into the design of the well to determine where that surface casing goes, because the surface casing, not the conductor casing, but the surface casing has to go down to at least 25 feet below the depth of this base of underground drinking water. So it's got to go down below that 10,000 foot, at 10,000 milligram per liter depth for groundwater. And this is something that's determined for each well because it varies from point to point in the state. And one thing that the Railroad Commission has done, which is a really nice, thing that they've set up to really facilitate the process, is that they've developed this web-based system for determining what those depths are. So you can go to this site and you can put in the latitude and longitude, or just point out the location on a map of where the proposed well is going to be, and it will determine what those depths are based on the best available science. It goes into this database of where the depths of fluids are at a certain water quality values. And so that's there's a address right here. And so that's something that if a well is going in, and you can go and take a look at that to verify that their construction issues are going to satisfy the need to get the surface casing below that depth. So all of these wells are designed to keep injected fluids in the injection intervals and stop them from getting into any underground sources of drinking water. So let's talk about what the water quality issues are associated with these, and focusing primarily on Class II wells. For Class II wells, the injected fluids are going to be, if they're disposal wells, those injected fluids are going to be oil field brines, and the brines that are associated with production of oil and gas. And typically these have salinity values that are anywhere from equivalent to seawater to up to 5 times the salinity of seawater. So one issue with that is if you have very small amounts of that get released and get into an underground source of drinking water, I mean, small percentages of it, that could potentially render that water undrinkable. If just on the salinity issues alone, they have to also realize that these are coming out of hydrocarbon producing zones, so they're going to have all sorts of other hydrocarbon related chemicals, potential carcinogens associated with them too. So there's a lot of potential issue for contamination of groundwater from very small amounts of these wells. Typically the permitting process that I've outlined should result in wells that will limit, if not eliminate, the possibility of any of these fluids getting up to the surface. But there have been studies that have identified impacts to surface, to underground sources of drinking water directly tied back to saltwater injection wells. And a number of these that have shown that it's possible. I don't think it's the rule, I think it's the exception that you're seeing this sort of thing around these wells, but it only takes one failure of casing or one problem with improperly cemented well to really damage a whole lot of water. And dealing with groundwater contamination, that's a difficult thing to clean up. And you can't just pump it out and clean it. Those issues can cause problems for a long time. So what are the specific mechanisms that can allow chemicals to get into the surface from an injection wells? Well, one of the obvious ones, it doesn't really have much to do with well design and well construction, is at these sites you could have surface releases. So if you have a saltwater disposal well that's disposing saltwater that's produced from a number of oil wells, typically what happens is there's a well that's centrally located and being providing services to a number of active oil wells in the area. And so water is either piped to it or it's carried in by tanker trucks. So there's all sorts of opportunities for a truck to turn over or for a pipe to leak. And pipes, if they're underground, they can leak for a long time and you not know anything about it. A lot of these will have surface facilities for storing, lots of storage tanks, and those storage tanks should have secondary containment around them, and those could leak. So there's all sorts of things that can happen to the surface that have nothing to do with the actual underground injection control permitting process, but they're things that you really should be aware of, especially if you're in an area where there's a lot of oil and gas operations going on. The second thing is that these wells are all permitted with a maximum allowable injection pressure, right? So they're not allowed to exceed that maximum pressure, and that's something that the TCEQ regularly checks on, and I'm pretty sure the Railroad Commission checks on that regularly as well. But that's not to say that operators couldn't, for a very short period of time, exceed that if their storage tanks are getting full or if they have a need or something like that. And the problem with that is that if that's exceeded even for a short period of time, there's a potential for hydraulically fracturing the formation. And if you frac the formation, then that could potentially open up an avenue from the injection interval into an overlying interval that could then get into another avenue and get to the surface. So this type of thing is rare. I've never really heard of it happening, but it's something that needs to be you need to be aware of that it's possible. One of the primary ways that you can get contaminants from these injection wells is through failure or improper construction of the casing or improper emplacement of cement. And that could include not getting enough cement in there. Typically, when you're cementing in around the casing, you drill the well and you set the casing in the well, and then you stick a trendy pipe or something all the way down to the bottom, and you pump cement in from the bottom and let it fill all the way up. And you just keep doing that until it flows out at the surface. And when it flows out at the surface, then you're pretty confident that it's filled up all the empty space in there, and you've got your annulus around the casing properly cemented in place. The other way to check that is that there will be a record, a cementing form, a form that shows how much cement was put in, and they'll list the number of bags, and each bag is basically related to a certain volume, like usually a cubic foot of volume. And so you can do a little bit of high school geometry. You take the diameter and height of the borehole, and then the diameter and height of the casing to determine the volume of each. Subtract one from the other, and you get the volume of that interstitial space, of that annular space. And you can compare that to the number of bags that are put in. And usually, when these things are properly cemented, what you'll see is that the number of bags that go in are usually about 25 to 30% more than the expected volume. And that's generally because when you drill those, the borehole, there's going to be places where the borehole is a lot bigger because it tends to, you have cave in. So there's going to be a lot more volume down there than just the two calculated one. So it's real typical if you see that they've circulated cement to the surface and that they put in like 1.2 times the number of bags that they would need to fill up that space, then that means that it's properly cemented, right? But there's always a possibility that there could be some flaw in the cement, or if it's an old well, that cement can degrade over time. The casing can degrade over time as well. And so you need to make sure that what they need to do is make sure that that's all cemented properly throughout the surface casing, that's excluding the underground sources of drinking water. Now, for the Class II wells, there's also that additional casing, what we call the intermediate or the long string casing, that goes all the way down to the top of the interval. And the Class II Railroad Commission requirements state that at the top of the interval, that all needs to be cemented for at least a 100-foot thickness. It needs to be completely cemented. The area in between, from the base of the surface casing down to the top of the interval, plus that minus that 100 foot of cement, that can all be left open. So the Class II regulations don't require that that be cemented. The only exception is that if there are any oil and gas reservoirs that are actively being produced, or any known oil and gas reservoirs, those need to be covered by cement as well. So they need to be sealed off from the intermediate casing. And even though you might think, well, that's just oil and gas reservoirs, they're not going to get up into the underground sources of drinking water. Well, that raises what the other potential issue is, and that's with abandoned wells nearby that have not been properly plugged and abandoned, that haven't been sealed off. So when you drill a well, and if somebody, say back in the 40s, drills a well and it's a dry hole, how did they abandon those things? Well, they would just weld a steel cover over the top and leave it open, or they'd throw a bunch of garbage down there, or fill it up with a bunch of gravel or something like that. So a lot of times those aren't open, and what you have is a direct pathway from whatever that formation is up to the surface. So that's a potential issue, and this is something that really is a concern throughout the state, and the agencies are trying to get a handle on all of the abandoned wells and make sure that they're all properly abandoned and properly sealed so that you don't have that kind of issue. So now, as I said before, there's opportunities for stakeholders, and specifically for, in your case, for groundwater conservation districts, because you can be considered stakeholders. There's opportunities for you to protest these applications. And I don't mean the protests like where you send your kids out in adorable outfits to hold signs around. I mean actually formally protesting and trying to get a stop to the application if you think that there is an issue with that application. So there's typically, for the Railroad Commission, we'll just talk about that because that's what you're most likely to encounter is issues with Class II wells. With the Railroad Commission, there's usually a 15-day period after filing in which you can request protesting status. And in my experience, if you miss that 15-day period, a lot of times they're pretty reasonable about letting someone come on board as an official protesting, or at the very least, they allow you to file opinions or statements or anything like that with the hearing examiners related to that application, even if it's after the 15 days. But 15 days isn't a lot of time, and it's really in the district's best interest to monitor what new applications are coming through. And if any come through, consider filing protests for them if they're in your jurisdiction. And filing protests, it's good even if it's not very likely that they're going to get even if it's not very likely that the protest is going to result in the application being rejected, it still can be a good idea to do that just to make sure that the applicants are held accountable for all of the different aspects of what's involved in the application process. And it can frequently get them to do things like install monitoring wells or get a more rigid and regulated mechanical integrity testing program, so they have to do that more frequently. Or maybe you can get their injection rates reduced to something that's more reasonable. So protests are not just about stopping someone from getting an application, they're also about getting someone, holding applicants accountable and making sure that they're doing all the things necessary to maintain to not potentially impact the quality of water in your district. So you should monitor these. It's my understanding that the Railroad Commission doesn't specifically send notifications to the districts whenever applications come in. I think there's a possibility that you can request that, but you should discuss this with your legal counsel. And if any of these applications come through, it's a good idea to get your hydrogeology consultant on board and discuss it with them so that you can get an idea of what the potential issues could be.
We are running short on time. I'd like to finish up real quick.
Okay. All right. Yeah, I think I'm almost done here, actually. I think I want like maybe one more. So these hearings, just a little bit about Railroad Commission hearings, they're not nearly as involved as other hearings. So my cat wants to weigh in here, so you have to ignore him. So the good news about that is that they're generally not as involved and they don't usually cost as much to pursue them. So it's usually worth pursuing them. There's a number of different grounds you could have for protesting. So whenever they file, all of those, all the forms that go along with it are available, and you could review those to see if there are any issues with the surface casing. Have your hydrogeology consultant see if there are any faults or abandoned boreholes in the area that you need to deal with. just see if there's actually really a need for a disposal, and make sure that there's any sufficient surface containment if they have a surface operation going on right there. So just to wrap things up, there's a potential for these injection wells to impact water quality. It's not really likely. I mean, there's regulatory procedures that try to limit that, but it is possible that it can happen. All of these regulatory processes are really associated with protecting underground sources of drinking water, but there are opportunities to protest, and you can look into those when those applications come through to see if there's reason to protest. And with that, I'll turn it back over to the moderators to see if there are any questions.
Thank you so much, Matt. And I think the cat was the perfect finish.
Yeah, he knows when I'm talking too long, so he came up to let me know.
Oh, perfect timing. We've got I'll see if we can do one or two of these questions.
Okay.
Oh, there it is. What's your opinion on the buffer zones for injection wells in the brackish groundwater production zones?
Well, the Water Development Board has just issued a contract for someone. I'm not sure who, because we applied for those contracts and didn't get them, but they applied for contracts for someone to come up with a more scientifically reasonable process for determining those buffer zones. As I understand it, now the buffer zone is something like 15 miles, which is it's excessive. And I know why they did it. They did it that way to be conservative until they could come up with a more reasonable method. But no, that needs to be something that's evaluated on more of a case-by-case basis. And I think it's going to end up being much less than the 15 miles. But that's I'm not sure how the consultants are going to do that. They have somebody on board who's doing that project, so I can't speak to it any more than that.
Okay, great, thank you. And we are out of time, edging into the break a little bit, so I'd encourage you to attend our happy hour tonight to talk to a few more people if you'd like. Thank you so much, Matt. Appreciate it.
Certainly, and anyone can feel free to reach out to me personally if they have any other questions too. You can find my email on Intera's site or get it from, it's pretty much out there. So.
Okay, fantastic. Yeah, we can get that information to anyone that needs it to have any more questions.